Hello, can you hear me? Perfect. My name is Eduardo Silva, and I'm a principal engineer at ARM. And let me check this because it's not passing the slides. There we go. Okay, so why I'm here? Actually, as an open source project maintainer, and I think as a maintainer, I face pretty much the same problems that you from a cloud perspective. If you are a GitLab user, it's because you want to improve all your DevOps experience, right? From CI/CD on how you manage your control version and all the details on all things of the ecosystem. When we think about any kind of platform to manage all these DevOps operations, we face the same problems with observability, with logging, metrics, and so on. And the nature of this talk is about to give you an overview on how do we solve logging for the cloud space, and I think that is pretty much what we are facing you in production. I'm part of the Flume Bed team. Maybe you heard about Flume Bed. It's one of the graduated projects of the CNCF, and I'm a maintainer of Flume Bed, which is a sub-project of Flume Bed, part of the same ecosystem. And the whole point about logging is not that logging is fun, right? Look at the dashboards, it's fun. Look at the metrics, it's fun, right? But what we really care about is about data, right? Logging is boring, but data is not. But data is not boring if you are able to extract the right value of your data. And that's why maybe you would like to put some, after your data collection, put database or any kind of tool that allows you to extract this value. Machine learning or any kind of data analysis that you can apply on top of it. And one of the things that we deal with analysis, oh, this is not passing the slides. I'm pushing the wrong button. No, I think that the clicker is not working. There we go. So in order to gather all your data, now your data is not just in one central place. Your data is maybe in different places. If you have a Kubernetes cluster, your data is created at different containers, generating log files or data in different places. And if you want to do data analysis, you need to centralize this information. And this is where this is the major challenge that we face. Years ago, if you are old like me, we used to use like, our syslog, and we just one channel of data and put all this data to one place. But now we have hundreds or thousands, and that's the complexity. So how do we deal with these challenges? There we go. So your data now comes from different sources. It's not just log files. We have TCP, UDP, or any kind of source of information. And if we talk about the embedded world, we also have sensors. And we don't have one sensors in one environment. Maybe we have 100, 1,000. So everything that we're talking about here is not just the normal logging that we know. It's about move data. How do we move data, and how do we centralize this data, and we are able to extract the whole information. And if you look at this, any kind of hardware or software, I need to send some event. That event can be a log message or call a record. That record goes to a database, and then we can do the further analysis. But if we have many sources of data, right, the things start getting slow because we have all this kind of concept of database, indexing, and you get a lot of delays on the same process. And latency, so how we can improve that? Because our goal, as I said at the beginning, is to be able to extract value from our data. Our goal is not logging. Our goal is to extract value. So how we do this? For example, we have a huge pipeline, right? We have to collect the data, filter the data, then process the data, aggregate that, and in the indexing part is where this is taking a lot of time, because a database is designed to optimize queries. But for that, the computing, the most expensive part is indexing, which happens when the data is being ingested. Or maybe if you create an index, after that, of course, it will take time. But if you want to improve data analysis, you need a different approach. And this is where different concepts, I'm going to explain pretty quickly right now, are trying to help, or we are trying to mix all of them in just one single solution. Are you familiar with stream processing? Have you heard about it? Please raise your hand. Are you Kafka users? Apache Spark? Kind of, okay. Stream processing is just the ability to process the data while the data is still in motion. In motion means in memory, right? Before this data, this byte hits the database because we want to avoid indexing. It's like on any environment. Sometimes we have the database, sometimes we have some cache on top of it to speed up the results. And with stream processing, we aim to provide specific results of data calculation before the data hits the database or any kind of long-term storage. And there are many ways to accomplish this. But in stream processing, we have some assumptions. Assumption is like our data has a structure, right? We are familiar with JSON. We are familiar with maps, with key and values. And that is a different concept of how relational databases are designed for. I'm not saying that one option is better and the other is worse. I'm saying that we have a different problem, and I'm saying that we need to find the best way to solve all the latency to gather value from our data. And as I said, every data is composed by a timestamp because a message was generated at a specific time, right? And also we have the message. We can think about syslog. Syslog saying priority, a timestamp, and the message, same thing. So if you think about JSON, this is a timestamp, we have a value, a temperature, and one becomes a key and the other the value. But in reality, what we have in our environments is that we have different records, different messages with different schemas, right? And this is not bad because this is a flexible way to generate your own data. But I'm sure if you are a developer, you are generating data in one format and somebody told the other person to create their own application, likely they are going to use a different key names and different things. It's not about how do we solve that everybody use the same schema, the same format for all your data, because that is impossible. People is trying to accomplish that, but it's like, it won't happen, right? But what we can do is how to adapt and solve that specific problem. So in stream processing, the objectives basically is how we can do fast data processing, but fast data processing without having a table, without having a database, and how this mixes with logging, because we're talking about different concepts. Maybe you have all this implemented in your own environment, but we need to find a better way to do it. So how this is accomplished normally? You have your application that are generating data. Then you have these events that are facing a stream processor. Can be Kafka with KSQL, could be Apache Spark or Flink or any kind of solution that is in the market. You generate your own real-time analysis results, and then your data also is being flashed to the database for long-term storage. But there's some specific things here. If you have a stream processor, you have to expose a query language, because if you're going to do stream processing, you need to say, please perform some calculation of this data for these specific keys that the value has this value. For example, over the data with a word equals blue, or a number is greater than 100. Or create a window of time and calculate how many records are matching this specific criteria. And for that, you need a query language for key selection, for filtering, aggregation, and data routing, and so on. Usually, people split this in two parts. The edge can be anything, right? But the edge can be, for example, just the application or a node or an embedded device sending messages outside. And in the cloud side, we have all our database, our cloud endpoints for data processing. That is one mechanism that everybody is using nowadays. The other approach that is coming up is that we are putting this kind of a log processor or aggregator, think about Flume or Flume Bed, right, on the edge side. Because if you have, for example, in embedded market, if you have 1,000 of sensors, you don't want to have every single sensor send data to the cloud. Because most of the sensors or constrained environments are not connected the whole day, right? They are losing data. So if you trust that your network is always up, you are doing something wrong. This is about embedded. Now, also in the cloud space, what people does is put some kind of aggregator layer, aggregate all the information there, where you have a good storage, good connectivity, and then ship the data out to the stream processor and all your cloud services. Think about Amazon or any cloud provider that you have. But how we can improve or make this better? Can we extend the stream processing? Can we make it better? If you have deployed Kafka, Apache Spark, or even think about Elasticsearch, by my opinion, I think that solutions are quite heavy, right? For some things that maybe you can do it in a different way, in a lightweight mode. So how we can make it better on that specific place. And let's discuss about logging. And logging is a nature of collect information and do something with it. Okay? But we're talking about stream processing, and we're going to see how this mixes with all these things. And we have the same thing. The logging challenges is that data comes from multiple places, and also data has different formats. If you have played with Apache, MySQL, Nginx, every single application has a different format for their own logging stuff. And maybe you can think, hey, this has a structure because I understand that this is a timestamp, this is a message. But if you pass that information to the computer, it's just an array of bytes, and that's it. There's no structure. A simple message that is generated by an application like, hey, GitLab, this message is not just the message. It's a timestamp from where this message was generated. This is a container message, the standard output from the container stream, and, well, the message itself. And if we think about different contexts like Kubernetes, when we need to append more context to our data, the simple message becomes something like this, because you need to identify where this data is coming from, which pod, which node, which container ID, or maybe you want to enrich all this simple message with annotations and labels that are coming from Kubernetes. So from logging, this is like a kind of complexity you have. So you have different applications, different formats, and you need to correlate all this with context. And we come up years ago. Well, we don't, but this has existed for years, a design which is called a data pipeline, which basically said you collect data from an input, you parse the data, you filter the data, you buffer the data because you don't want to lose records, and then you route that data out to a database or a central place you're going to do your own analysis. And this design was used to build Flume Bed project and the project that I'm going to talk about, which is called Flume Bed. It's like a full open source projects that are part of the CNCF that allows to solve all these data collection and logging problems. Flume Bed was started in 2015, originally for embedded Linux, but a few years after that, most of the people from the cloud space started to use the project to solve all the logging collection needs because of low memory footprints, low CPU footprint, and the capabilities that we have for security and so on. It's written in C language. Yes, it's not written in Go, it's not written in Rust. We can talk about later outside. That is a common question. Yeah, why not Rust? Why not Golang? Well, it's in C. But it's really good because you have a pluggable architecture, and when you have logging, plugins are everything. Because if you have different sources of data, likely if this year you have 10, next year we have different new source of data. And you need to extend and adapt your logging pipeline. So how do you do that? With plugins. And we have built-in security, and we have currently more than 50 plugins available. Logging basics is like application generate a record. That record or message has a timestamp, a message, as I said before, but internally, we don't do this in JSON. Okay, we do use like a binary format for that because you don't want to do data processing using parsing byte by byte. So we use message packs, which is like a kind of binary JSON, was created years ago, and Flume Bed and Flume Bed are based on top of it. So application generate a log. This log goes to the log processor. And how this works internally. Oh, we have a format issue, but no problems. So every time that we get any records, the records are grouped by tags, because maybe you have data that's coming from Apache, data that is coming from syslog, then these go inside the storage the main storage engine, and then it's routed back to different output connectors. What is an output connector? Elasticsearch, InfluxDB, Amazon S3, or any kind of endpoint that you would like to send your data out. And why this is important? Because if you have many sources of data which are different, and you have many output destinations, you need to correlate this information in a unified format, and that is message pack. So in the input, we know how to read and encode information, and in the output, how to decode this for the expected payload. Actually, Flume Bed is being deployed like 200,000 times every day, which is a lot, so a couple of millions per month, if you do the math. And it's being widely adopted by AWS, Google Cloud Platform, and recently, a few weeks ago, Datadog is also relying on Flume Bed for data collection. And Flume Bed in the cloud is quite known. If you are familiar with Kubernetes, imagine that, for example, that node is a Kubernetes node. What Flume Bed does basically is just to read all the container logs from the file system and then go to the master API server to collect all the metadata that I just demonstrated before. And then we can ship the data out to your own Elasticsearch. Likely, if you are from operations, what you are seeing is your old application container logs with all the metadata, because you want to query, show me all the logs from this application that a label is red. But maybe that application is replicated in many nodes. We have replicas in the container. So this is a way to group all the information together. So, and we reach the endpoint in the stream processing and logging, and how do we solve this all in data processing world. There is one thing why we want to extend stream processing, and that is performance. Everybody likes performance, right? But performance can be something different for each person. For me, performance could be a rate, could be a low memory footprint, or I don't know, any kind of metric that you have. And how we can make it better. In Flume Bed 1.0, we started implementing its own stream processor. That means that you can do logging, normal filtering, and data processing in the edge, inside your own tooling that you have in your cluster or your service or device. So this was the original approach that most of people is using, and what we are doing is something like this, merging all the stream processor in the same logging tool. And think about that when this is running in memory, it's maybe using 5 megabytes of memory, or 10. You are not deploying a Java stack, because that we can use those Kafka KSQL or Apache Spark for more intensive tasks. And it's maybe if we have something that we can do on the edge, we can improve on many areas. And it's basically the same pipeline, right? So having that, the only difference is that after we store the data in our storage, of course, we put the information in the stream processor. And one of the capabilities of the stream processor is that it can create new streams of data with results. Because maybe you don't want to send all your data to the cloud. Maybe you just want to send the results of specific queries. And how do we accomplish this? So input plugins generate streams of data. We know that beforehand. Also, we have right after that phase, we have the stream processing. And we implemented a full SQL query engine on the stream processor. So you can run SQL queries in the logging tool. Yeah, there's no database, there's no table, there's no indexing. The only difference is that you don't have tables, but you have streams of data, right? But you can do the same thing. Select key A, B, and C from stream something, where, and some conditions. And we can create different kind of queries. One achieve the other. You like aggregation? We're going to talk about that.
I don't like aggregation. I'm just asking a question.
Yeah, how do we solve it? Yeah.
What does it do?
Aggregation. For example, an aggregation in the query or aggregation in the file system?
In the query.
In the query, imagine that you are getting data from sensors. You have one sensor that is sending samples, like 100 samples per second. Do you want to send all the samples to the cloud? Or maybe you want to do a window of aggregation of 1 minute, perform calculation, and just send the average. That's why aggregation is important, because you can do the math over a period of time while the data is being ingested, and you just send the results out. So, and part of the aggregation is that you can do the common SQL functions like count, max, min, average. And also you can group by the results, because maybe you have a different kind of data identified by a device ID or anything like that. And all of this is running in C language, and there's no database, it's just one binary. And also, we have the ability to create, one thing is data selection, and the other is create a new stream of data. And if you look at this is pretty much similar from KSQL. Actually, most of our team, we are taking a look at how people is solving the problem, and we're trying to replicate kind of the same features in the best way possible for us and for our own users. And one of the advantage of this is all this stream processing. I would say that there are three things. One is performance. And when I say performance, this is really important, because if you're collecting data and centralizing the data to do data analysis, maybe your results will be available after a couple of minutes. Here, if we do the data processing on the edge where the data is being generated, you can get the results in a fraction of seconds or milliseconds. Imagine that you are monitoring a web service that is generating some transaction from credit cards, and maybe you want to trap who is doing a duplicate of a transaction by mistake. Maybe you can say, okay, I'm going to run a query for a period of window of 10 seconds, and if the same credit card is issuing the same transaction with the same amount within these 10 seconds, trigger an alert, cancel the second one, or do something with that. In the opposite case, you will have to ingest all the transaction details into a database in the cloud service, wait for data indexing, and run a separate job to trap this kind of exception. As a use case, and this is something that you can run on the edge and get better results. And this is just the beginning. And I say just at the beginning because we started with data collection. We extended to data processing. Now we are doing stream processing. And of course, the next step will be like long-term storage. We're implementing kind of a concept which is called snapshots. We're going to merge those features in the next week. Snapshots means, for example, create a persistent storage number of record for the last minute or for the last hour. So you can be able to, anytime, to go and say, please show me the last snapshot of data that happened at this time or during this period, just for data analysis, audit log, security, and so on. Now that from a logging perspective, there are many use cases. One of them is troubleshooting, but security people tend to be a bit freak about all the details, so we need to solve that problem too. And performance is important, and that's why it's really important for us to gather all these details and all this information when they are just happening in the cloud. There's no other solution in the market that is doing this at the moment. This is like a new concept. The reception from the community has been really good. So if you have any comments or questions, I will be glad to talk to you outside after this presentation to get your feedback. Thanks so much. If you have some questions, we have time. We have 7 minutes. Sure.
Do you only do processing on a single node, or can you accumulate IDs from different nodes in case, say you have a load balancer that sends a usage request to different servers and you want to do processing on all the users' requests?
Okay, the question is if you can do the processing in just one node, or if you have a load balancer and different nodes generating data, can you do the processing for all this group of data or nodes? Yes, the answer is yes, because Flume and Flume Bed are designed to work in a network mode, so they can process the data and also they can talk to each other. So you can collect data from Flume Bed, and aggregate all of them in just one Flume Bed and do extra processing here. So it's up to you. Yes, it's possible.
Is there any possibility of joining two data streams together?
Yeah, we are joining our ideas on how to implement that because yeah, it's very challenging because the data is just flowing from multiple sources. So when you say a join in a database, you assume that the data is already stored is already there. But when implemented, this kind of join will be in memory. So we need to create this kind of, it will be a similar concept of windows of time, because you want to say, hey, my join will do from this time to this time, and all the data that join in this fraction of time will be part of all the data set. So we are thinking how to implement that, but yeah, it's in the roadmap. No ETA, please. Don't ask for any ETA.
Sort of follow-up question. How about joining of, say, statically side-loaded data? Like you roll out your stream processor with like a table that has static data in it. Could you join perhaps against that?
If you're accessing a database, if you have a database with data?
It's, let's just say there's like a table that has like 100 rows of reference data, like mappings of state names to state abbreviated codes, like New York to NY, for instance, and you want to join against that.
Yeah, you can do it. Of course, so the thing is how to solve first is how to extract the data from these places. If it's a database that we don't have a connector to, you can create your own input plugin, extract the data, and run the processor on top of that. And Flume Bed can run as daemons in Kubernetes. You can run it from the command line as a Unix tool. So it's quite powerful. And also, I don't think that I mentioned that, but for example, you can create many streams of data, like create stream with a SQL statement. And in the next stream creation, you can consume the result from that one and do something with this. With the streams, you can process the data, and also you can say for all this data, attach a different tag, and that tag is going to Elasticsearch. Different tag go to Hadoop, different tag go to. So it's quite flexible because we aim to implement a full backbone of data, so data processing and data management in a lightweight mode, of course.
Thank you.
You're welcome.
I'm wondering if you support like externalized checkpoints or externalized state, like some of the other big stream processors do. Like if the entire system goes down, do you have any type of failure recovery right now or in the future?
If a system is down where the stream processor is running, or?
Yeah. So say you're doing an aggregation, and it's got that window of 10 minutes or 10 seconds or whatever. And the entire system goes down. When you boot back up, the aggregation no longer has the rest of the stream in context, right, for that time. Do you support checkpointing that say, hey, we've gotten to this watermark or this point in time, and then moving onwards?
Okay.
Or you just have to start from scratch?
Sure. The question is if we can handle failures scenario when we're doing data processing, right? Yeah, we have different kind of mechanism for that. For data ingestion, when we collect the data, you can put the data either in memory by default or also in the file system for persistency. So when the data hits persistence in the file system and go to the routing phase for the output plugin, we don't remove the data until the data is successfully flushed, okay? And if it fails, we have a retry logic. We have our own scheduler, so you can configure that, how many retries, or maybe retry forever, and so on. For for stream processing, we are just working in memory now. So if you have a window of 1 minute and the process crashes, you're going to lose that data at the moment. We are not using persistency, but that's a plan. It's in the roadmap to implement something like that.
I think we have time for one more question.
One more
Eduardo,
question?
yeah. If there is one.
Last one.
Great.
How are you guys measuring the performance of Flume Bed to make sure it's keeping up with all the processing that you're talking about, so that you don't, in case you need something more beefy, like we're saying, like Kafka or something like that?
Okay, how do we measure performance? And there are two angles. The first one is that we expose an HTTP endpoint, and we also support Prometheus endpoint, so you can hook and pull metrics from Flume Bed, and every input plugin counts number of bytes, number of records, number of failures, so you can see how your data is flowing. Okay, sometimes data is not flowing because it cannot flush the data, but you will realize that from using this external tooling. Now, from a development perspective, we just created a few weeks ago a new project called Flume Bed Perf with different tools to measure how many records from different sites we can ingest over TCP, over Intel, and capturing memory usage, CPU usage, and it's something I'm going to showcase in the next KubeCon, which is in November. So from a developer angle, also we care a lot about performance. So internal, how many records you can process per second, if the records are from these sites, or for the different input plugins or source of data. Okay.
Great, thank you.
Thank you.
Thank you, Eduardo.